All right, in this video, I'm going to cover section 3.8, Poisson distribution. So this is the last the distribution, probable distribution with discrete random variable. We're gonna learn in chapter 3. So Poisson distribution, the random variable x represent number of events that occur within the interval. So the we're gonna we're gonna deal with the event in the finite the length or just interval, okay, or finite time interval, something like this, okay. So the let me let's see example 3.6, okay. So to the better understand the Poisson distributions. So and then also using the through the example 3.26, we're gonna define the problem mass functions mathematically, and then we know we're gonna figure out we're gonna better understand the what random variable x means in the Poisson distribution. So the example 3.6, the talking about wire flow. Okay, so flow occur at random along the length of the thin copper wires. So definitely, thin copper wire. So we're gonna see the restrict the I mean we're gonna figure out the number of flow occurring at some finite length of copper wire, okay. And then here the random variable x means the number of flow in a length of t millimeter of wire, yes, okay, t millimeters. So now let the average number of flows per the millimeter is lambda. So what's the lambda? Lambda maybe just 1 or 2, okay, or just 0.5, okay, this is any real number, positive real number, okay, per millimeter. Then using that, average, using the lambda, we can figure out the mean value, okay, the mean number of the flows in length t, okay, which is lambda times x, right? So for each 1 millimeter, the average number of flow is lambda. Then average number of flow in t millimeter going to be lambda times t. It makes sense, right? So now probability distribution of x. So first one to figure out so the probability distribution of x, we're gonna divide 0 to n, t millimeter copper wire to n subintervals. Okay, let's say the length, I mean equally, okay, and then length of each subinterval lambda t. Okay, says lambda t, which is t capital T over n. It makes sense, right? So now, if lambda t is less than epsilon, you can say epsilon is a really small number. Okay, so if lambda t is really small enough, then probably that more than one flow occur in a subinterval is negligible. It makes sense. If it's just for example, let's say t is just 1 millimeter, and the n equals 1,000 subintervals. If you just divide the 1 millimeter to the 10,000 subintervals, then lambda t is really, really small. Then the probability that more than one flow occurs is almost zero, right? It can be ignored. Okay, so then the next one, we can interpret the assumption that the flows occur at random to imply that every subnumber has the same probability of containing a flow, say p. Yeah, so here we assume that flow occur random. It means that the probability that flow occurs, the each subnumber is going to be equally likely. Okay, so it means that we can say that probability that the flow occur for each subinterval must be equal and say p. Okay, so p is the probability that the flow occur at each the subinterval. Now assume that the occurrence of a flow in a subinterval is independent of flow in other subintervals. Yeah, makes sense. Okay, so the probability that think about this in the first solving number and the second solving number, the probability that flow occurring second solving number will not be affected by what the probability that flow occurring in first solving number. So now then we can now we see that we can consider that the what each solving number as trials, and the outcome is what flow or not flow. So binomial, the Bernoulli triangles. So each is the event it, you know, according, flow for each subunit can be considered as a Bernoulli triangles. It means that what? So now, then the probability distribution of x, what's x? Keep in mind this, in a Poisson distribution, x is what number of events that occur within the interval, okay? So now it means that in this example 3.26, the random variable of x is the number of flow in the length of d of wire. So then the probability distribution x, which means that what number of the flow occur in the copper wire length t can be interpreted as what? The binomial distribution of x. Okay, and each sub-interval generate an event, flow or not. Okay, so now then what? So it makes sense, right? So now then the e of x expected value going to be lambda t can be must be equal to n times p. Okay, so p is a lambda. You see that then p is equal to lambda t over n. Okay, keep in mind this. T is what? Length. Okay, length of copper wire, and the lambda is average number of flow in per millimeter. So lambda and t, um, we can figure out lambda and t from the problems. Okay, so then n also must be given. So p is unknown. Then we can figure out p using that formula, lambda t over n. Now let's figure out the probability mass functions. So then see here, probability mass function x is equal to lowercase x is equal to, is that n combination nx and the p to the x times 1 minus p to the n minus x. This is what actually, that's the what binomial, PMF or binomial distribution, right? And the n goes infinity, yes, because let's see, let's see, because n goes should goes infinity, because you can see that the lambda t must be really small enough so that we what the probability that one more deflow occur in a subinverse is negligible. So that the each subinverse we only expect the one the flow or not, so that the we as you can see that the each subinverse generate an event or not. Okay, so that the each event can be considered, each subinverse can be considered as the Bernoulli trials. Okay, success or failure. Remember that. So now in order to the lambda t is really small, enough, the n goes n must go approach infinity, right? So we use a limit. Okay, so now then the ncx combination of n and x gonna be this. Okay, by definition of combination, and then we express p in terms of lambda and t and n. So we plug in this fraction into p. So we're gonna get this. Okay. So now the here first one, see the lambda t. Give me a second. So lambda t to the x power and the x factorial. Okay, we just taking them out. So we got this one. Okay, and then we're gonna separate the breakup that term to the 1 minus lambda t over n to the nth power right there, and then 1 minus lambda t over n to the minus x power, right? And then yeah, so now is what are uh they are left over, you see, n times, this is the n times through the n minus x plus 1, and then you see that n to the x power is here. Okay, and then now you see that, because look at this limit is what limit this expression as n goes infinity, but that fraction is not involved n, so we can bring it out. Okay, so right here, Okay, and then excuse me, and then we just copy 1 minus n, lambda t over n to the nth power, and then 1 minus lambda t. Okay, and then now see we're gonna to decompose that fraction as n over n, n minus 1 over n, like this. We can express that big fraction as product of partial fractions. Okay, I'm sure that you learned about the partial fraction. So the how many terms here? X, because you see that n to the x power. Okay, how many terms in the top? X, n minus 1 through the what? N minus x plus 1 can be expressed as what? N minus, let's see, what? The x minus 1, right? Okay, that makes sense. So then n is the first term, n minus 1 second term. Okay, then what's this? This is what? n minus 1th term, right? Nth term, right? Okay, nth term. So how many terms here in the numerator? N. Okay. So now then, give me a second. So now the all right. So now the first one. I mean, let me keep going. So now the n goes infinity. Okay. So then, if n goes infinity, I mean, look at this. This one actually 1 minus lambda t over n to the nth power. That's a limit of. Okay. This is the definition of what? Using the definition of exponent natural number. Okay, we can that must converge to e to the negative lambda t. Okay, and then the second term, what? As n goes infinity, lambda t over n approaches 0, so we get 1 to the minus x, right? And then all terms, because n over n is 1, and then this is 1 minus 1 over n. The second, this one is 1 minus 2 over n. This is what? 1 minus, the x minus 1 over n. Okay, so the what? So we got this one. It's a 1 and 1 minus 1 over n. So that's what we got this. And then limit of each term as n approaches infinity converge. I told you this one is what? E to the negative lambda t. Okay, by the definition of natural number. And then this is what? 1 to negative x, right? Because n goes infinity, this fraction approaches 0. So 1 to negative x. 1 to the negative x, for any x, 1 to negative x is 1. Limit of 1 is 1. Limit of this guy is 1. Because 1 over n, 2 over n, 3 over n, x minus 1 over n approach 0 as n approaches infinity. So each term converges, right? In that case, the limit of the product of each term is equal to the product of limit of each term. That's one of property of limit. I'm sure that you're learning in calculus 1. So we're going to apply that limit into each terms because limit of each term converge. Okay. So now then we know the limit of the second term is just 1, and then third term 1. So limit of second term through the last term equals what? 1. So that is equal to what? Lambda t to the x power over x prime times limit of the first term, which is e to the negative lambda t. So that's what we got this. Okay. So now, finally, we got this e to the so finally we got this. This is the what? PMF of Poisson distribution. Okay. So for given lambda and the length or inverse, length of time or the inverse, length of inverse, the PMF gonna be this. Okay. So now we can apply the let's figure out this, and then see example above can be generalized to include the broad or the array of random experiment particles of contamination in a semiconductor manufacturing that flows in a roll of textile and then that calls to a telephone exchange. Yep, and the power outage in the atomic particles emitted from the spaceman. So now, but in general, probability x is greater than 1 approach 0 as an approach infinity. It makes sense. Okay, that's the one of the assumptions, right? Okay, so now when you construct the PMF, and the probability x equals 1 going to be lambda times delta t as n approach infinity. Yes, it makes sense. So now the event in each subuniverse is independent of other subuniverse. We saw that, right? A random experiment with this property is called the Poisson process, and these assumptions imply that the subuniverse, if and only if, approximate independent Bernoulli triers. I told you, so we could consider this each subuniverse as the the Bernoulli trier. We told you, right? So number of triers is gonna be n. The success probably gonna p. Yeah, that's what I explained. What I have explained about it. Okay. Now, yeah. So we just summarize the PMF or Poisson distribution. The random variable x is what number of event in a Poisson process. Okay. So in a view of binomial distribution, x is what number of success, right? Okay, is a Poisson random variable with a parameter lambda, and the f of x is this. Okay, we just prove it, right? We just show that. Now, now next one, the proof here. Okay, so is this really f of x is really satisfied the three property of the probability distribution function? Yes. First one, the sum of f of x must be equal to 1. Yes. So that's sigma. This is what? The series, right? Sigma x goes 0 to the infinity, and then this is f of x, right? Is this really converts to 1? Yeah. Why? Because see that e to lambda t, we're gonna take out e to negative lambda t out of the sigma, and then lambda t to the x power over x factorial. This is what? I mean, sigma of this guy is equal to what? E to the negative e to the lambda t. Okay, I'm sure that you learned about the series in calculus too, right? So definition, we could express e to the x as like this using the what? The Taylor series, or we can say Maclaurin series. Okay, right? So now then this is the converts to the e to the lambda t. Okay, the e to negative lambda t times e to lambda t is 1. Proof is done. And the primary lambda is the mean number of event per unit length. Okay, one in the example 3.26 was 1 millimeter, but in general just unit length. Okay, it is important to use consistent unit for lambda and t. It means you have to unify the unit of lambda and t first. For example, if lambda is 2.3 floors per millimeter, then t should be expressed in millimeter. Okay, keep in mind this. And then let's see. Then let's see the expected value, and then variance. Okay, and then look at the example 3.27. Okay, so mean and variance. All right, so we're gonna use starting from the definition. We're gonna start from the definition of expected value. So sigma and then x times f of x. Okay, so why we start x equals 0? Not x equals 0, but 1, because when x equals 0, we're gonna get 0, right? So we're gonna we can ignore the case that x equals 0. Okay, so and then the lambda t, we're gonna take a lambda t out of sigma. We got this. So now I'll see. You see that this one, lambda t to the x minus 1 over x minus 1 factorial, right? This is what e to the lambda t, right? I mean sigma. Okay, all right. This is the e to the lambda t. So, or you can say to be more clear, okay, we could change the variable by setting y equals x minus 1. The x minus 1 factorial is going to be y factorial, and the while x move from 1 to infinity, y move from 0 to infinity, right? So see that this is what? E to the lambda t. Okay. Before doing that, I just we took out e to the negative lambda t out of sigma. So we got lambda t. So expected value of Poisson distribution is what? Lambda t. Okay. So now next one, to figure out variance, variance is what? E of x squared minus mu squared, right? So we need to figure out E of x squared. So now then, using the definition of expected value, we got this. Take out lambda t. Okay. Pretty much a similar. We use a similar strategy. What we use in the expected value, right? So now the let's say x is equal to x minus 1 plus 1. Okay, well, x minus 1 plus 1 is what? X, right? So now then, let me see, first one. Then we change x to x, what? Give me a second. So we express x as the what? This one. Okay, this is x as x minus 1 plus 1. Okay, 1, this. Okay. Then the distributing that fraction, okay, inside the bracket, we're gonna get this x minus 1 times fraction and then 1 times that fraction. That makes sense, right? Okay, just distributing, okay, right? So we got this. Now then, what? Definitely, this is we saw that, right? This is what? E to lambda t, right? Okay, and then this. Give me a second. Now let me go. So on here. Okay. So now then, lambda t times that's gonna be what? This is gonna be e to the that's exactly what? This is the definition of e to the x minus 1. Okay, but letting y equals x minus 1, we can say this is expected value of y. The expected value of y is what? Lambda t. Okay, this makes sense. Okay, so now then, because you see that what y e to the lambda expected value of y is a lambda t. Back to here, e of x is equal to lambda t. You see that lambda t. That expected value is not involved what? The random variable. Okay, all right. So that's why e of y is lambda t. Okay. Now, what does that mean? Actually, what is y? Y is x minus 1, right? E of y minus 1 is what? Lambda t. Okay. So now the e of x is lambda t. E of x minus 1 lambda t. E of y is lambda t. It makes sense. Okay. So now then the second term is lambda t times what? This is what? E what? You see that here? This is what? E to the negative lambda t times e to lambda t, right? Okay. Why? Because this one. Sigma of that fraction is what? E to the lambda t times e to negative lambda t is what? 1. So we got lambda t squared plus lambda t. So now then, thus what? The variance is going to be lambda t squared plus lambda t minus lambda t squared. Wait a second, where we got this? Lambda t squared plus lambda t, that's a e of expected value of x squared minus expected value square. Okay, that's the formula of v of x. If you don't get it, please go back to the this the section 3.1 and yeah, section 3.1. Okay, look at this. Okay, so the variance, look at the formula of variance. Okay, so we got the lambda t. So it's here interesting is this expected value and the variance, they are equal in a probability distribution function. Okay, information on the variability is easily obtained. Conversely, if the variance of count data is much greater than the mean of the same data, the Poisson distribution is not good model for the distribution of random variable. It makes sense, right? So the you know the variation of the data is much greater than the mean of the same data, then yeah, if you use a Poisson distribution, then we're gonna get the that Poisson distribution doesn't represent the data. Okay, so we cannot use this one as a good model because E of x and V of x is equal. Okay, so then now next one we see the example 3.27.